Welcome back to Codex. Our speaker today is Robert Weber, who is a postdoc at Caltech. Dr. Weber is an expert in randomized numerical linear algebra, and today he'll tell us about rocket-propelled Cholesky. Take it away, Robert.
Hello, everyone. Thank you so much for the nice introduction and for the invitation to come give a talk. Most people call me Rob, so feel free to call me Rob. Like Dustin said, I'm currently a postdoc at Caltech, and I'm on the job market this year, so who knows about the future. Here is an overview of what I'm going to talk about today. The talk is structured to be really pedagogical at first, and then it becomes more mathematically complex as I keep going, and we get into the nitty-gritty of the proof in the last few slides. So let me start with the pedagogical part. Why do we even care about this stuff? Low-rank approximation is defined as the act of compressing a large matrix, think 1,000,000 by 1,000,000, to a low-rank factorized form, think rank 100 or rank 1,000. It is useful because it has a lot of applications. It can speed up kernel methods, which are used for prediction, interpolation, and clustering. I also just learned that it's useful for deep learning because there's a growing recognition that neural network weights and updates to the weights are approximately low rank. So if you're looking at, I guess, GPT-3, and you're trying to fine tune it for some learning task, it often suffices to make a low rank update to the weights. That's an interesting connection I just learned about. Our motivation at Caltech was we want to provide a fast, robust, low-rank approximation method, particularly one that's easy to implement, and then also has mathematically guaranteed accuracy. And the results that I'll tell you about today are randomly pivoted Cholesky, which you could also call rocket-propelled Cholesky if you prefer, is the most efficient method for approximating PSD matrices that we know with an entry-wise axis model. And that means you're counting every time you evaluate a single entry of the matrix. And I'll show you examples to make this real. Here is a QR code, which you can generate online, apparently, to link to your papers. So that's cool. And here's pictures of my co-authors, many of whom just leveled up because it's a new school year. So Ifan is now a Courant instructor. He used to be a PhD student at Caltech. Ethan moved up from third year to fourth year PhD, and Joel Trop remains once and forever a professor. Kernel matrices are a particular type of PSD matrix, positive semi-definite matrix, that I'm going to use for all of the examples today because they're evocative and you can think about kernel matrices both as mathematical arrays of numbers, but then also as representing data and similarity between data. And I like the two perspectives. So it's going to be defined as a positive semi-definite PSD matrix with entries lowercase aij equals k, xi, xj. Kxi, xj is a bivariate function. It measures similarity between data points, xi and xj. Often 0 means they're totally dissimilar. 1 means they're exactly the same data point. It doesn't have to be that way, but it has to be what's called a positive definite kernel function, which means you evaluate it on any finite set of data points and you get out a PSD matrix. An example, which is really standard, is what happens if you have some clustered data points. And then you decide to define a kernel matrix using what's called the Gaussian kernel or the square exponential kernel. Kxy is defined as the exponential of the negative square distance between x and y, divided by 2 times a bandwidth parameter, sigma squared. We've got 6 data points in this example. 1, 2, 3, 4, 5, 6. They're in 2D Euclidean space. And so here's just the x1 and x2 coordinate of the 6 data points. It's a 2 by 6 matrix. And already you can kind of see something crazy going on, which is we're trying to do data analysis, and we're starting out with a small 2x6 matrix, and we're blowing it up to a 6x6 matrix. We are creating 3 times as much storage. We are doing a lot of extra calculations to try to gain insight into what was originally a much smaller object. And it works. In this case, I've sorted the data points just by the x1 coordinate from smallest to biggest, but maybe the data doesn't come pre-sorted. Maybe it comes all jumbled together. And you can imagine that by permutations of the kernel matrix, you get into a block diagonal form, an approximately block diagonal form, where the blocks on the diagonal are pretty close to 1, indicating high similarity between data points. There's a red cluster of similar data points, a blue cluster of similar data points, and the off-diagonal entries are much closer to 0, indicating dissimilarity. So the kernel matrix, after the right permutations, is going to reveal cluster structure in data. Does that part make sense so far? There's a lot you could do. And this you might have to take on faith, or like maybe you've had exposure to these before. We can use kernel matrices for prediction, interpolation, and clustering. It always boils down to a linear algebra problem. We solve least squares problems for prediction, predicting functions from data input-output pairs. We solve linear systems for interpolation between data points. And we need to calculate eigenvectors for clustering. So linear algebra is important, but linear algebra is challenging. The matrix size is n by n. Remember, n is like 1,000,000. N is the number of data points. Direct inversion or eigendecomposition algorithms to solve the above problems would require order n cubed operations. So that's 10 to the 18 operations. Data movement is also really hard. With most of your computers, like I imagine a lot of folks have Apple computers or Windows computers, and maybe you've got, I don't know, 32 or 64 gigabytes of RAM. If you have a matrix that's 10 to the 5 by 10 to the 5, you might not be able to hold that matrix in your random access memory. You can't hold it in your laptop. You can't generate it in MATLAB or in Python unless you're using some extra program that stores the matrix to disk. And then moving the matrix in and out of disk gets really hard. So think 10 to the 5 is where your system starts to run into difficulties. At least mine does. The idea is we're not going to do that. Okay, we're not going to deal with the whole 10 to the 5 by 10 to the 5, 10 to the 6 by 10 to the 6 matrix. We're going to replace A with a low rank factorized approximation. And the running question is, can we? How well does it work? What bounds can we prove? We specifically want to use what's called a Nystrom approximation or a column Nystrom approximation. It's defined for a PSD matrix A as a factorization. It's an approximate factorization where you multiply A colon S by A SS dagger, A S colon. And here I'm using like MATLAB notation, where S is just some set of indices from 1 through n, and there's k of them. A colon S means you're picking out the submatrix with those selected columns. AS colon has the selected rows, ASS has the selected rows and columns. ASS dagger is the Moore-Penrose pseudo-inverse of ASS. And a picture is worth 1,000 words. Here's the picture. So you take the columns, you divide by the submatrix with the selected rows and columns, you multiply by the rows. And it recovers an approximation which has the right dimensions. And like a lot of nice properties, way more than you might think. So the first one makes sense. I mean, This is your approximation. You're literally taking linear combinations of the selected columns to try to approximate the matrix A. So yeah, your approximation lies in the linear span of the selected columns. That part is clear by construction. The matrix is PFD, and that's also pretty clear by construction. You take a PSD matrix, take its pseudo-inverse, you conjugate it by some selected columns. It's not immediately clear that it has a PSD residual, which means if you subtract A hat from A, you get a PSD matrix. You can think of A hat as approximating A from below in the PSD ordering sense. And then what's really not clear a priori is it has the smallest PSD residual possible of any approximation from below in the PSD sense. So it has a smaller PSD residual in the sense of PSD ordering than any other approximation satisfying 1 through 3. All this is to say that Nystrom approximation is really cool. Column Nystrom approximation is a natural approximation. It's valid for any PSD matrix. So it doesn't have to be, kernel machine learning. Any positive semi-definite matrix you can approximate this way. It's related to something that folks have surely heard about, but maybe not in quite the way that we think about it, which is called Cholesky decomposition. I think when most folks learn about Cholesky decomposition, they think about taking apart a PSD matrix into like the product of a lower triangular and an upper triangular matrix. Is that how folks sort of remember it? Yeah. There is a stepwise description of Cholesky decomposition, though, where you just look at what's happening after like the first 1, 2, 3, 4, 5, et cetera steps. And you would start with a rank 0 matrix, so just the 0 matrix, and a residual that's the whole matrix A. And you would gradually approximate from below using an iterative procedure for I equals 1, 2, 3, all the way to K. You have to select some column index. This would be called pivoting. Choose a pivot in the context of Cholesky decomposition. It's just some number between 1 and n. And then you're updating your approximation by adding a rank 1 matrix. And you're subtracting that same rank 1 matrix from the residual. So always you've got A hat I plus AI equals A. This is just the low rank approximation and the residual component. And the low rank part is nice. You're looking at the current residual, taking the selected column times the selected row divided by the selected diagonal entry. So maybe it's the simplest thing that you could think of that has the right dimensions and is a rank 1 update defined by the selected column index. I have introduced this as a stepwise procedure. Column index S1, then column index S2, then column index S3, then column index S4, etc. But the order actually doesn't matter at all. At the end, you get out the Nystrom approximation defined by the set of selected indices, S1, S2, S3, all the way to SK. So you could have done it backwards. You could have gone SK, SK minus 1, SK minus 2, SK minus 3. You would have gotten the same approximation in exact precision arithmetic. So that's another cool aspect of Nystrom approximation. It's pretty cheap because if you implement it smartly, you only need to look at the selected columns. You only need Kn entry evaluations to form a rank K approximation and order K squared n arithmetic. You don't need the whole matrix. This is important for kernel methods because it costs a little bit to evaluate that kernel function on, say, high dimensional data for each point. That would require a lot of operations. You don't need to do that. You just look at the selected columns. Let's show a visual example. Go back to the clustered data points, the red points and the blue points. Let's look at the first 2 steps of the Cholesky decomposition. This is a nice example because you can see the 2 different perspectives. There's like the linear algebra perspective where you've got an array, a 6x6 array that you're approximating, but then you've also got data points. You've got 6 data points. And whenever you select a pivot, you're selecting a data point. The first selected data point is this star data point in red. This is number 3, because I've arranged them by the first coordinate, the x coordinate. And so you're grabbing the third column of the matrix, dividing it by the third diagonal, multiplying it by the third row. That is your rank 1 approximation. This is your residual. We can see another nice property of the Nystrom approximation revealing itself, which is that the whole third column and whole third row are now 0. And I'm using this convention that people use a lot in linear algebra where like blank entries of a matrix are 0. And you can also see that this rank 1 approximation is doing a pretty good job at taking these red components that used to all be pretty close to 1 down to 0. It's doing a very good job of reducing the residual in this red submatrix. It's not doing as good a job at reducing the residual in the blue submatrix. So what's the best point to choose next?
The last one?
The last one? So I'm doing something terrible here, just like, to get people to sit up a little bit. I'm asking like people in the audience a question. And not only that, I'm doing something really terrible. I don't myself know the answer. Okay? But I applied the randomly pivoted Cholesky procedure, which will show satisfies some nice error bounds. And the next point that was selected was not quite the last one. It was this point, which is actually the 4th one. But yes, it was part of the blue cluster. I mean, I'm really heavily implying you want some data point in the blue cluster, because then, you've got a rank 2 approximation using the 3rd column, the 4th column, and the residuals are just really small. In the trace norm, the residual is nearly 0. So you're doing a very good job of approximating the matrix in the trace norm. I believe that these points are close together, so that wouldn't have made too much of a difference which one you choose. I'm not sure whether it's better to choose one of these or one of these. If you know the answer, tell me. So that worked, right? The last part of the first third of my talk is an existence theorem, which says, yes, this often works. And it often works in the sense that there exists an efficient column Nystrom approximation for any PSD matrix with fast decaying eigenvalues. So this theorem is fundamentally relating the existence of these good low rank approximations by column Nystrom approximation to the eigenvalue decay of a PSD matrix. I'm attributing the existence theorem to Guruswamy and Sinup in 2012. For the experts in the audience, the proof is constructive using determinantal point process sampling. It says fix a PSD matrix A and let A sub R be an optimal rank R approximation, the best one you could possibly get, which comes from an R truncated eigendecomposition. Keep the top R eigenvalues, set all the bottom ones equal to 0. You get out a rank R approximation that's as good as possible. There exists a K column Nystrom approximation, where K is typically going to be bigger than R, that's almost as good as that best rank R approximation in the trace norm, up to a 1 plus epsilon fudge factor. And how big do you have to take K? You have to take K bigger than R over epsilon, plus R minus 1, for this existence theorem to guarantee that there is a really good column Nystrom approximation. So if the eigenvalues rapidly decay, this right-hand side is going to be small for low R values. Like, let's say they're exponentially decaying. Oh, I got a question. Oh, no. Actually, that's if you would like to sign up for the chat, sign up here. Okay, I didn't get a question. But please, chat people, you can ask questions. I only have 28 slides, so I actually have time to like
Is this
go back and
existence
forth.
theorem proved using the probabilistic method?
Yeah, it is. Isn't that cool? The probabilistic
That is
method is determinantal point process sampling. It's amazing. The right-hand side is small if these eigenvalues are decaying exponentially. Imagine the eigenvalues are e to the negative I for the ith eigenvalue. Take R to be like 10 or 100. This object is going to be order e to the negative 10, e to the negative 100. You have a fantastically good approximation, even taking epsilon equal 1. So you basically just need like 2R columns and you can get a fantastically good approximation. 20 columns, 100 columns, 200 columns. It's sharp. I can construct a matrix A that cannot be approximated with fewer than R over epsilon columns. I mean, it's very nearly sharp. Like, I accept there's a little bit of room between R over epsilon and R over epsilon plus R minus 1. But that's sort of minutia, especially since people often focus on epsilon being rather small. 1 over 10, for example. The existence theorem does not lead to a practical algorithm. How can we choose columns that capture the action of A in practice? That is the rest of the talk. Does anyone have questions about the first part? Okay, cool. So let's choose some columns. This is a busy slide because I wanted to include all of the necessary background. Here's the background. We got this Cholesky decomposition. We're building up a low rank approximation, keeping track of the residual, iteratively selecting a column index, doing the rank 1 update, and subtracting the rank 1 component from the residual. And what's buried here is select a column index. How? Which column? Which data point? That's the only parameter that this algorithm needs. In the right, I outlined 2 classical approaches. The first one's called the greedy method. It's essentially the same as pivoted QR. You look at the residual, you look at the diagonal entry, pick the biggest one, and that becomes the next pivot in your algorithm. The next method, which seems so silly, like on the surface, but is incredibly often used in practice and does surprisingly well, is the uniform sampling method. We don't know how to pick the next index. Let's pick it uniformly at random. Maybe you want to do this sampling at random without replacement. But, with a very large matrix, that doesn't gain you much. Our alternative is called randomly pivoted Cholesky, where we pick the next pivot probabilistically with probabilities proportional to the diagonal entries of the residual. This is a PSD residual, so all of the diagonal entries are non-negative. So you normalize them by their sum, so it's a probability that sums to 1, and sample one of the indices according to that probability vector. There's a generalization which I like because I have a background in statistical physics. I like to think about a Gibbs distribution with different temperatures where you're sampling the next pivot proportional to the diagonal entry raised to some p power. And here P would be like an inverse temperature parameter. So the greedy method would be the P goes to infinity limit. Like I think of that as the 0 temperature algorithm. Uniform sampling is the P goes to 0 limit. I think of that as the infinite temperature parameter, the infinite temperature algorithm. And then RP Cholesky is literally setting P equals 1. You might wonder why this even makes sense. In all of these Gibbs distributions, you're more likely to select the pivots where you have large diagonal entries in the residual. And this matters because there's a generalized Helder's inequality, which I still didn't fix that typo, geez. The off-diagonal element squared is less than or equal to the product of the two associated diagonal entries. So I'm missing a square sign right there. It says, though, that if the diagonal entries are small, the off-diagonals have to be small. A large off-diagonal cannot hide. It has to be associated with large diagonal entries. So large diagonal entries are really giving information about the whole associated column, the whole associated row. And this is true because of the positive semi-definite structure. It wouldn't be true for a symmetric matrix at all. Examples. 2 Gaussian kernel matrices, one of which is a smiley face, made of 10,000 points in 2D space. The eyes are only made of 100 points. So here's the smiley face, and it has a couple eyes, and the eyes only make up 1% of the data. Little beady eyes. The outliers data point, you have to stretch your imagination a little bit. Imagine 10,000 points in 20D space, and I'm taking a random 2D slice, and 50 outliers, which are the points that you're really seeing in gray, lie far away from the others. So I don't know, imagine the center of the universe with like lots of planets all hovering around each other, and then a few that just got far flung. 0.5% of the data is far from the rest. I said that Colin-Nystrom approximation can only work if the eigenvalues are decaying quickly. So I'm showing you the eigenvalue decay with a Gaussian kernel. Really, really fast decay for the smiley face. Slower decay for the outlier data. You notice a step-like structure? That step-like structure, I haven't completely puzzled it out, but I think sometimes when I give this talk, people actually know why it's a step-like structure. It's 20 large eigenvalues, and then you step down. And then there's 400 at the next level. And then there's probably 8,000. And remember that it's 20D space. So if that immediately makes sense to you, explain it to me in the chat, please. But it is a step-like structure. It's slower decay, though. This example, we cooked it up to show why you don't want to do greedy and you don't want to do uniform. Greedy does probably the most terrible thing that you could do to the universe. It forgets about 99.5% of the data that's right at the core. It flocks to the outliers. And as a result, the trace norm error when approximating the kernel matrix is quite high. There are several other methods in the literature, DPP sampling and RLS sampling, uniform sampling, and now our new RP Cholesky that all do much better at recovering the structure of the universe. They mostly pick the planets at the very center. And then uniform sampling does the most terrible thing that you can do to a smiley face. It misses the eyes. So now this smiley face is, I don't know, just not as happy, I guess. And trace norm error is significantly, significantly higher when you miss the eyes. There's another method called ridge leverage score sampling, RLS sampling, which is nearly identical to uniform sampling in the aspect that it misses the eyes and has a high error. RP-Cholesky does fine for both examples. Think of it as a trade-off between exploitation, it nabs the small features in the data, and exploration. It explores the bulk of the data, which is located at the center of the universe. That's for intuition. Folks in computational linear algebra care a lot about runtime. There are methods for selecting centers, also called pivots, also called landmark data points, which are exorbitantly slow. Determinantal point process sampling is a beautiful mathematical method that has not been implemented efficiently. When you run it in dppi, it does not give you an answer. For the SMILE data with k greater than or equal to 60, it returns an error that says cannot give you an approximation. Matrix is approximately low rank. So the code won't run. When it does run, it needs 80 to 100,000 kn evaluations empirically. RLS sampling, ridge leverage score sampling needs about 3 kn evaluations. I'm just counting the number of kernel entry evaluations you need to form a rank K approximation. And then the other methods are like really cheap. Uniform sampling, you wouldn't even need to look at the diagonal, just the selected column, so it's exactly KN entry evaluations. Greedy selection and RP-Cholesky, you do need to look at the diagonal. If you know a priori it's all ones, then it's exactly KN, but if you don't know that a priori, it's K plus 1N. So, okay. RP-Cholesky avoids the failure modes, pretty cheap in practice. These are like silly examples. I'll just give one example, which I think matters. This is my favorite algorithm in the world, kernel spectral clustering. I find it so cool. It's a nonlinear clustering algorithm that can do very well in some modestly high dimensional spaces. You use a kernel matrix K to guide clustering of a data set. And the way that you do it, which has a lot of rich interpretations for stochastic people, is you form the matrix D to the negative 1K, where K is the kernel matrix and D is the diagonal matrix of row sums. So you make the matrix row stochastic. So it could be interpreted as like a transition matrix, like a hopping matrix for a finite state Markov chain that's hopping around your data from one data point to another. Calculate the dominant eigenvectors, the right eigenvectors of the hopping probability matrix, D to the negative 1K, and then just cluster the rows of V. This is now an N by M matrix using K-means. So the hard part is step 2. Calculating the dominant eigenvectors of a matrix that could be 1,000,000 by 1,000,000. How do you store the matrix? How do you calculate its eigenvectors? A lot of folks would compute eigenvectors at a cost of n-cubed operations by using a function on their computer like np.linaug.eig. Or if you're clever, maybe you could figure out how to do np.linaug.eig and get the same answer. But it's still n-cubed. You can try to run land shows, get just a few of the top eigenvalues and eigenvectors. That would be order n squared k. Our approach is to approximate K and D using RP-Cholesky. So just replace that kernel matrix with K hat, get its row sums, compute the eigenvectors at a cost of order K squared N. I'm applying the method to identify the metastable states of a protein called alanine dipeptide. Metastable states are the states that a protein stays in for a long time. And then there's rare transitions to a different state. These are important for understanding the dynamics of proteins and mini proteins and ultimately designing medicines to affect the functionality of proteins. The data comes from trajectory data from Monte Carlo sampling, molecular dynamic sampling of the protein system, containing 250,000 snapshots. Each snapshot contains XYZ positions of 10 non-hydrogen atoms. We don't usually care about the hydrogens because they're small and light and they stick to the other ones. The direct method, you can't do it. You can't do spectral clustering of 250,000 data points. You have to subsample the data, and often in the literature, codes run for more than a day. Maybe that's okay. You know, maybe you don't need your computer every day. But it's nice to know there's an alternative procedure that runs in 10 seconds. And with k equals 150 columns, it's not only forming a very nice approximation of the kernel matrix, it's giving 9 times to 14 times smaller errors than uniform RLS and greedy sampling. This picture is the 4 clusters in alanine dipeptide. And it's a sneaky picture because you're analyzing like 30-dimensional data. You're clustering 30-dimensional data. And through those clusters, it then later becomes apparent that you can look at a couple dimensions, which weren't even in the original data set. Like these are nonlinear functions of the coordinates, and match up these nonlinear coordinates to the discovered clusters. So this is the sort of result that spectral clustering enables. Here's a plot that shows error, the rate of misclassification. So that's like the fraction of cluster assignments you get wrong as a function of the approximation rank. Remember, it's a 250,000 by 250,000 matrix. And if you're using this rocket-propelled Cholesky, you're already starting to get well lower than 1% misclassifications with just k equals 150. And this is because of the underlying rapid decay of eigenvalues. That's what enables this mathematically. It's interesting to see what other algorithms do wrong. Greedy, you could probably imagine what's going to happen. It flocks to outlier data points, which are far away from all the others, and doesn't do a good job at representing the bulk. For some reason, it creates another, like a weird cluster right here, which isn't physical. Uniform sampling goes where most of the data points lie, and that just happens to be in this very, very populated region. There's only a single data point that's sampled over to the right. And so, you know, of course, you're not going to do a great job. Ridge leverage score sampling is like kind of similar to uniform. It doesn't have any data points here, for example. These are periodic coordinates. They're angles. They're called dihedral angles. And then RP Cholesky does a good job. It gets the right clusters. So this ends the practical the like applications portion of the talk, and the rest of it's going to be mathematical. So does folks have questions? Okay. All right, this is the part that I'm really stoked to give like this audience in particular, because the mathematical analysis was, for me at least, a fun experience where I learned a lot, and I found the results to be very satisfying. So the question I ask is how many columns k are sufficient? That a column Nystrom method guarantees a R epsilon approximation, which means you're nearly as good as the best rank R approximation up to a 1 plus epsilon fudge factor for every single n by n PSD input matrix. So this is a worst case analysis, but we're going to average over the random choices in the algorithm. So this is going to be a bound that'll hold for any PSD matrix A, no matter how nefariously chosen. And it's going to show how well we do on average at approximating that matrix over the random choices of pivots. The answer is that RP Cholesky ensures a R epsilon approximation after accessing a modest multiple of R over epsilon columns. Modest multiple. Okay, what does that mean? The table shows the best available bounds for the various methods in terms of R, epsilon, N, and eta. Eta is the relative error in the best rank R approximation. So it can be a pretty small number. It can be like 1 in a million. A lot of these bounds are terrible. The lower bound is R over epsilon. So that's the best you could ever hope to do. We get R over epsilon plus R log 1 over epsilon eta. Recall that eta is the relative error in the best rank R approximation. And like most folks who do algorithmic analysis, we believe that the log factor doesn't kill you. In particular, it satisfies log 1 over eta is less than 37 when eta is as small as machine precision. For all like the actual data sets where I've evaluated eta, log 1 over eta would be more like 6. So this bound is pretty comparable to the best you could possibly do, up to a factor of, maybe 6, if you set epsilon equals 1, for example. And there's no prefactors. You'll notice that the available bounds for RLS sampling have a prefactor of 136, which, is probably not sharp. So how'd we get this? This was the main result of our archive preprint. Fix a PSD matrix, let A sub R be the best rank R approximation from an R truncated eigen decomposition. You get out a K column Nystrom approximation that satisfies the R epsilon guarantees as soon as K is greater than or equal to R over epsilon plus R log 1 over epsilon eta. The proof uses some standard strategies like dynamical systems, and then some pretty interesting linear algebra strategies called matrix monotonicity and matrix concavity. So let's go through the details together. We have to start with the algorithm. What does it do? It is fundamentally looking at the residual matrix, A, I minus 1 at each step. It's looking at the diagonal of the residual matrix to sample a new entry, and then it's making a rank 1 update where it's taken something away from that residual. So the residual is getting smaller in the PSD ordering sense. So the algorithm is a Markov chain. It's a matrix valued Markov chain on the residual matrices. Time homogeneous matrix valued Markov chain. And so what you might want to do with Markov chain theory is you might want to look at how the Markov chain evolves under one step. Let's look at the expected behavior under one step. Let's look at the expected one-step residual, given that you start from a state A. Well, that's defined as randomly sampling a pivot according to this probability distribution. So the expectation, we sum over the probabilities, we multiply by the rank 1 matrix that gets taken away, and we notice a cancellation between a numerator and denominator term, so that the expected one-step residual is A minus A squared over trace A. A matrix-valued function with a lot of nice properties. It's monotone and concave with respect to the PSD ordering. So it's got these matrix monotonicity and matrix concavity properties, which are like exactly the same as the scalar case, except you have to make all of your letters capital and bold and replace all the less than or equal tos by curly less than or equal tos. That would be the definition. So this is the core of our analysis, this little lemma. We can apply it recursively. to get a bound on the trace norm residual, where the left-hand side is an expectation over a random quantity, and the right-hand side has nothing to do with probability. It's literally just a deterministic function, this residual function applied k times to the matrix A, and then take the trace. This lemma removes all the probability. And the way you do it is you say, oh, okay, concavity. We can use matrix Jensen's inequality. We can look at time I plus 1, what's the expected residual matrix, condition on the residual matrix at time I, and then we calculate that this is going to be the expectation of phi acting on AI. With concavity, you're allowed to move the expectation to the inside to get an upper bound. Apply this display recursively, and you can see the expected residual matrix. This is a whole matrix on the left-hand side, is bounded from above in the PSD ordering sense from phi acting on the expected residual at time k minus 1, which is bounded from above by phi acting on the expected residual at time k minus 2. And you keep going and you get phi acting k times on the original matrix A. And then last, you throw a trace on the left-hand side and the right-hand side. It respects the PSD ordering. So, okay, that's going to turn into a less than or equal to. And you find that the expected trace norm error is going to be bounded from above by the trace of phi acting k times on A. So that's the end of the probability part. And the rest, I mean, I was able to work it out. It's a clean analysis, but it is slightly involved. There's 6 steps. You first notice that this phi, remember that's A minus A squared over trace A, doesn't depend on the eigenvectors. Once you take the trace, it doesn't matter what your eigenvectors were, it only matters what your eigenvalues were. So you can take A to be diagonal. So that's a nice reduction. And then, okay, I mean, it's invariant under reorderings of the indices, and it's concave. So you can average together a bunch of indices and it only makes it worse. Average together the top R indices, average together the bottom n minus R indices to explicitly reveal the worst case matrix, which is diagonal. And the first R entries are all equal to A over R. The bottom entries are all equal to B over N minus R. So it's just like a 2-cluster problem. This is the worst case matrix in the sense that it gives this quantity as bad as possible while keeping fixed the sum of these and the sum of these. Worst case is achieved by averaging. And then you notice, okay, like we know what phi is. We have explicit formulae for how these diagonal entries are going to evolve under step 1, step 2, step 3 of applying phi to this diagonal matrix. AIs and BIs are decreasing sequences. I'm not showing you exactly the details. They come from the definition of phi as phi of A is A minus A squared over trace A. And I am showing you an upper bound you can get where you just say like the B part, those small diagonal entries, well, they were decreasing over time. So let's just bound them from above by their initial value, B naught. But let's pay attention to those big diagonal elements. And let's bound them from above by an A bar K process defined by this difference equation. Now, I don't know how to solve difference equations with a nonlinear right-hand side. I did some Googling and I couldn't figure out how to solve this difference equation. I think that in general, nonlinear difference equations, someone I guess who had worked on this before told me that they're pretty hard to solve. I do know how to solve differential equations like univariate ODEs, right? And so we noticed that at each instant, t equals 0, 1, 2, et cetera, the discrete time process a bar t is going to be bounded from above by a continuous time process, which is literally take this difference equation and make it a differential equation, make it an ODE. And the reason the comparison holds is because, like, you look at this right-hand side and you say, okay, like it's decreasing faster if a bar k minus 1 takes a higher value. There's sort of a monotonic right-hand side. And then we use separation of variables to solve the ODE by direct calculation. X of t is less than or equal to epsilon, b is 0 for any t that's pretty big, that's bigger than or equal to r over epsilon plus r log 1 over epsilon eta. So that's it. That is the proof. I know that some of the details were buried, but it establishes this error bound, which doesn't need any prefactors because it came from rather tight analysis of this matrix valued function in the worst case. And to summarize, rocket-propelled Cholesky, we believe, is a smiley face of an algorithm. It can be programmed in a few lines of code. It requires k+1n entry evaluations and order k-squared arithmetic. In all of our experiments so far, RP Cholesky improves on alternative algorithms for low-rank kernel approximation. So it is the best way to approximate a kernel matrix. If you want to do low-rank approximation in the context of kernel machine learning, do RP Cholesky. And we've proven that it achieves these near-optimal approximation guarantees. It's nearly an R over epsilon approximating algorithm. Thank you for your attention. Does anyone have questions?
All right, let's thank the speaker by smashing that reaction button. This is how we show our appreciation in the post-COVID age. I'll stop the recording here.